Even when we regularly think about geological timescales and cosmological timescales, it's easy to lose track of the depths of deep time. So if the boring billion had been the boring 2 billion, our civilization now wouldn't come around for another billion years later. And if that were the case, by that time the sun would be too hot probably, and certainly human beings would not have evolved in their present form, and it would well be the case that no intelligent life would have been evolved. If it had been the boring 1.1 billion years, our civilization would still be 100 million years in the future, or the boring 1.01, and once again things would still be way in the distance for us. Even the difference of a mere 10,000 years, which is the entire length of civilization on Earth, would make a crucial difference whether there's a civilization 10,000 years before us or 10,000 years after us. That would make a really big deal for what we think of as pure emergent complexity. And there's all kind. That's just one. The boring billion is just one example of a timing mechanism in geological history that could have been very different. And if it had been different and then just a different time scale, then we'd still be offset from any other peer. But if it was different and the difference meant that no peer evolved, then that would partly explain our isolation. And in terms of timing, if the humanity is an early fluke, it would push back, civilization on a peer star like an F or G class star far enough that it would change the habitability of the planet on which, in the habitable zone, and then, as I said, the civilization might not arise at all. So, timing is crucial. Astrobiologists have focused recently on M dwarfs and K stars, which could be habitable for tens of billions of years as optimal spots for life to develop. But obviously, in a universe that is 13.7 billion years old, there haven't yet been billions of years, tens of billions of years for those stars and planets to have developed their life. So if we think of it as a timing issue, this is all something that lies in the future and will maybe comprise the bulk of the Stelliferous era, which will eventually come after the Krauss and Scherer end of cosmology. And the timing issue that may be unusual, that results in us as an outlier complexity, is the unusualness of biospheric evolution taking place so rapidly on a planet orbiting a G-class star. And the same processes, more or less, formally speaking, that happened on Earth could happen on a planet orbiting an M dwarf or a K star. And if you've got a biosphere that's potentially habitable, this habitability window stretches out for 20, 30, 40 billion years. It's not a big deal if the boring billion is the boring 2 or 3 billion, or even 4 or 5 billion, and the other later stages of life also continue to be stretched out over billions of years, and maybe you only get a biosphere as mature and with as much biodiversity as Earth's until it's twice as old or an order of magnitude older. If it took Earth 4 billion years to become the biosphere as it is today, 3.8 to 4, as those are usually the earliest dates given. An order of magnitude longer would be 38 to 40 billion years. So there you got the whole higher end of the spectrum of habitability ranges for M and K class stars and their stable habitability windows. So one order of magnitude up, you've already exhausted that. If you go 2 orders of magnitude up, and it takes, on average, 380 to 400 billion years for a biosphere like Earth to evolve, then it's only going to be outliers that result in biological emergent complexity and basically nothing else. If a red dwarf star had a planet in its habitable zone, and that red dwarf star could remain viable as a star for tens of billions of years, even if the red dwarf star had periods of severe flaring that would end up completely sterilizing any planet in its habitable zone, because the window of habitability is so long, you could have a habitable world completely sterilized and repeatedly sterilized for 10 billion years, 20 billion years, and then when conditions are right, if they are right, you could still have a biosphere evolve. Now, there are several qualifications and conditions to this. If radioactive materials play an important role, whether in keeping the world warm or more directly, as in the nuclear geyser model of the origins of life, then the decay of radioactive elements over the periods of the planet's lifetime would make it less likely to produce life as the more time that elapses. And similarly, if a flaring star blows away the atmosphere of a habitable planet, and there's no more outgassing and no more possibility of outgassing that would produce an atmosphere, then nothing's more going to come of it. So it has to maintain the conditions, the rudimentary conditions of habitability, and then, if the flare just kills off life, or if the atmosphere can come back, or if nuclear materials don't have to play a crucial role, or if they're still viable to play their role, there are still ways that a biosphere sterile for billions of years could have a biosphere. Or if the flares kill off everything but deep subsurface microbes, those subsurface microbes could just stay there dormant for billions of years, alive, very slowly alive, and then eventually when conditions come out, when conditions are right, then they can multiply and create a habitable world, or a biosphere, I should say. And in our own solar system, say, as a possibility, we don't know yet, that early in the history of Mars, we know that there was probably liquid water on its surface. Say it was a world that involved rudimentary microbial life, and then the planet freeze-dried itself, and then that life on the surface essentially came to a halt. But if it's preserved in the deep subsurface depths of the planet, eventually, when Mars becomes warmer again, when the sun begins to expand, there'll be a short period of time during which the expanding sun would make Mars just right. Initially, it would start warming up, and then it would be just right, and then it would be getting too hot. But it would pass through a period of probably hundreds of thousands of years, I'm guessing, maybe millions of years, because I don't know how quickly a sun growing into its red giant stage grows, but there would be a period of time during which Mars would be just right for habitability, and if there is a subsurface biosphere, it could then assert itself again and become a surface biosphere. This is like an extended period of dormancy or like stagnation. So it would like be a boring billion that lasts for many billions of years, maybe 5 billion years, maybe 10 billion years, maybe 20 billion years, and still could assert itself as a more luxuriant surface biosphere. Though it is also possible that a subsurface biosphere might become so locked into a stagnant, slow-moving subsurface biosphere that even when conditions change, that there's no longer much change in the biological content, and it's unable to make the transition to surface and other forms again. That's just mere speculation, but an interesting idea.